Hello, my name is Millicent Warner, and I will be presenting my Lab 2 video on lines of charge. First, let me go over the schedule for the video. I will start by introducing some key ideas, formulas, and data from the experiment. I will then show my preliminary calculations in GlowScript model to visualize the results. Next, I will find the results, or more specifically, the magnitudes of charge and electric and gravitational forces on the tape. Lastly, I will answer the thought questions provided in the instructions. What if we used a point charge model instead of distributed, as well as which estimate is closer to the real value? The first of the fundamental principles before I get into calculations is Coulomb's law, which is an equation to calculate the electric force due to two charges that are a certain distance away, each with their own charge. The formula is a constant times the product of the two charges divided by the distance squared and multiplied by the direction vector. Next, an electric field indicates an area surrounding a charged particle that other charged particles would feel a force within. It is important to note that an electric field is dependent only on the source of the field, not the particle experiencing the field. The formula is a constant times the charge of the source divided by the distance squared and multiplied by the direction vector. In other words, the electrical force is equal to the electric field times the second observation charge. We can extend this formula to the concept of a charge evenly distributed along a rod. If we are looking at a rod of total length L, we can take tiny sections along the rod and treat them as point charges. Note that the more pieces that we take, the more accurate our estimate will be. The formula ends up being as follows. Lastly, and the most intuitive of the principles, is the gravitational force, which is the attractive force between two objects. For this lab, we will use this formula to calculate the gravitational force between Earth and the upper piece of the tape. The formula is the mass of the tape multiplied by the acceleration due to gravity in the negative y direction. A few last notes before we begin. Again, we will be utilizing lines of charge, or a collection of point charges calculated individually on a line. Also keep in mind the principle of superposition, which states that we can add vectors by component, meaning electric fields do not block one another. Now I will introduce the procedure to estimate the amount of charge on a U-tape. I will start by making two U-tapes by swiftly pulling the upper tape tab off of the base tape on the table. I will then check that the U-tape have negative charges by seeing if repulsed by a pen. After this assertion, I will hold one U-tape below the other until the top one floats. At this point, I will record the distance between the U-tapes. Here is a visual of the physical model used in this experiment. The two U-tapes repelled each other as they both had the same negative charge. In this way, the tapes are expected to repel each other with equal magnitudes. Note that U-tape B is considered to be floating when there is no movement in the y direction, or no net y force. In other words, the electric force and the gravitational force are equal in magnitude and opposite in direction. Let me state some of the important values regarding this experiment. The length of both U-tapes ended up being around 0.215 meters, and the mass of each was 0.000215 kilograms. The width of the tapes were 0.023 meters, and the distance between the two tapes once flotation was achieved was around 0.0225 meters. First, I recognize that when the top tape is not moving, the magnitude of the electric force will equal that of the gravitational force. I then used the formulas of each force and set them equal to one another and plugged in the necessary values to get a charge on the tape of 2.4065 times 10 to the negative 8th coulombs. The code to visualize the data runs as follows. I entered in all of the initial values needed to begin the experiment, including K, the gravitational constant on Earth, the charge of the proton, the mass of one tape, and the charge of the tape. I then created a function to calculate the electric field from a point charge to be used later. Next, I initialized the electric fields on the top tape to 0 vectors and set proper scales. Then I iterated through the code to calculate the electric fields and forces from tiny point charges along the tape. Finally, I added these individual electric forces together by superposition to get the total force. In short, I found the magnitude of the electric force was around 0.01265 newtons, and the magnitude of the gravitational force was around 2.1092 times 10 to the negative 3rd newtons. Let me make 3 assumptions about this lab. Firstly, I am ignoring the air resistance on the moving tape. Secondly, I cannot treat each tape as if all of its charge were located at a single point at the center of the tape. Instead, I am taking small segments and treating those as point charges. Thirdly, I am assuming that each U-tape has the same net charge and that charge is evenly distributed along the tape's length. What if we used a point charge model instead of a distributed model? Going back to my calculations during Lab 1, I found that the charge of the tape was about 1.114 times 10 to the negative 8th coulombs. However, I found during Lab 2 with the distributed model that the charge of the tape was about 2.4065 times 10 to the negative 8th coulombs. The first value represents a point charge model from Lab 1, and the second value represents the distributed model in Lab 2. The charge in the distributed model is probably larger because it takes into account every small point charge of one tape with every small point charge of the others and adds them together. In other words, it does not reduce the complexity to only one charge located at the center of the tape. Which estimate is closer to the real value of charge? The difference between the two estimates are the mathematical and conceptual approaches. One models a tape as a point charge at the center of the length, and the other models it as a charge uniformly distributed along the length. In real life, the charge on the tape more closely resembles the distributed model, so it presents a more accurate estimate, because more interactions are accounted for. Thank you for watching, and here's a link to my GlowScript code.